Hello, welcome to another problem session. Uh, instead of doing a problem, we are going to clarify some of the things you should know about angular momentum. So to start with, we're gonna address this question of angular momentum of a particle. So we have a particle of mass m, and that is moving at time t with speed, maybe it's velocity, let's call it velocity. We need the direction. So we have a particle like that. So you might say like particle is going in this path and it happens to be here at time t, and its velocity is in that direction, tangent to the trajectory, and that's how the velocity occurs. So we want to know what is its angular momentum. So it's kind of related to linear momentum. So let's see. So it has linear. Often we don't say the linear, but it's just momentum for this, and we'll say P is mv. So how much what is its angular momentum? Well, that's not such a straightforward question. So for angular momentum, we would say what is its angular momentum and that's not the end of the story. We have to qualify it about some point O. So I need to say where is the point O? Well, maybe point O is over here. So I have to actually give this point to you, that there's a point about which I want the angular momentum. Okay, so we are going to use letter L. Letter L, and it is a vector for this quantity. Okay. So how do I define it? Well, why do I need this point? Well, I actually need this this displacement vector, which we'll call R. This R at this point, of course the particle is over here, some other points R will change, but we're looking at this point you have R and this. So this is instant by instant, right? So at this instant, angular momentum will be equal to R about O, R cross P, and P is the regular momentum. So this is the most fundamental definition of angular momentum, and this is a cross product, and I will not explain it to here, but I just use it. So let's look at some simple examples. So here is a XY plane. So this is an example, XY plane, and maybe something is going in a circle. Maybe you're driving a car around a circle, what have you. So it's at this point at time t, and maybe O is at the center. That point is center is O. So I want to know what this will be, and the velocity is going in a circle, so tangent to the circle will be this direction. So let's look at the directions. So we have, say this is the x-axis, the velocity will be parallel to the y-axis, So this is parallel to the y-axis. That's the direction for velocity. and this is R, and this is V. So R has got the magnitude R along the, let's the radius of the circle be, radius be R's. So this will be the radial vector at this time, at time t. And then velocity vector is going to be along the y-axis, so velocity vector will be some v y hat. V doesn't have to be constant, you know, we're just looking at something where this is going in a circle. So in this example, I've got L equals to m. These are the scalars, so R and V, and x hat cross y hat. Now this is z hat. So angular momentum, although this object is moving in xy plane, actually any object is moving in xy plane, so angular momentum about a point in the plane will always be in the z-axis. So this is actually m r v z hat. So you can actually see very nicely that is going to be z direction. Angular momentum will be along the z direction, and there you can see immediately that this must be the one way to look at the circular motion is the axis is actually perpendicular to the circle, right? So this is so this tells actually the axis around which this thing is moving in a circle, right? A point is moving in a circle. If instead of like this, and I don't have x and y and z, anything like that, so another example would be, instead of going in a circle, if something was going in this circle, a tilted circle, but it's going in this circle, well, you can immediately say that this is going to be, angular momentum will be in that direction. So if something is going in this circle, it's going to be perpendicular to this, perpendicular to that area of the circle. And of course, magnitude wise, L will be equal to mass times the speed v, and the radius is r. It's going to be like that. Let's look at another example. A particle is moving in that direction. So say this is the velocity and this is the mass of the particle, and the velocity is that way. Velocity is that way. And I want about this, my O. Well, you'll be probably surprised. There's some little bit of surprising that if you this is the R, and when you work out, this is the closest point, right? So let's call this B. You will find that L of this object moving like that about O is going to be a vector coming out. So if you look at into the direction will be into. Okay, so like if you have an arrow pointed in, it's like arrow pointed in using right hand rule for R cross P for this vector, taking a cross product. So the L magnitude, and the magnitude will be just B times V times M, will be M V B. How did that happen from this definition? Well, let's work that out. So if I if you look at this V is in that direction, so we have this angle. So let's call this angle, let's call it theta. So I have a 90 degree plus theta, that's the angle between them. So you'll have a V times R. So let's work out the R cross P will be M R cross V equals to M R V, and then sine of 90 degrees plus theta. Well, 90 degrees plus theta will be just cosine theta. So this will be MR V and into into the page direction. So this you can write down into the page. Let's see, direction is some unit vector u hat. So that's the direction for the u hat into the page. So RB cosine theta u hat. Now cosine theta with R will be just this. If this side is equal to R, then this, and because this is 90 degrees, this will be so the R and cosine theta just gives me MB V u hat. That's how I got that. Okay, so that's angular momentum of a particle about this point, and that's the definition of an angular point particle. But you know, this is all written in terms of linear velocity, and we would like to write this as a rotation because I want to use angular momentum as a rotation. So how would I convert this thing into a rotation? So to convert this information to rotation, we go back to this picture, and let me redraw the picture. So here's a picture, and at that time t am here, and this is my point O, and velocity vector is that way and the radial vector is that way. So you can see that at a little bit later time the R will be pointed that way. So this is R at t plus dt, and this has magnitude v delta dt, and it's in this direction. So this is the delta R vector is in that direction. Let's call it v hat direction, in the direction of the velocity, right? Then if I want to think this angle being d theta, then this will be very small, and I can consider that to be an arc. I mean, consider it to be actually a circle. This and that distance will be difference insignificant. So this is like an arc of a circle. So this is actual v dt distance. This is the arc distance, should be equal to the radius, which will be almost identical to R, and there will be d theta. So if I take so this was in some plane, and if I define d theta to be vector to be perpendicular to the plane, so let's call it this is xy plane, and perpendicular axis is z. So this will be like a z hat d theta defined like that, and v is v in the v hat direction, which is in xy plane, and r is some r which is also in xy plane. So when we do this, we are going to you can use I'm not going to prove it, but you can prove that v vector is actually equal to d theta vector over dt cross r vector. And this is what we call the angular velocity vector. So that's the angular velocity vector across r. So this you can see the in terms of magnitude, you can see v equals to omega r's if they're perpendicular to each other, right? So over here, but this gives you the full direction. Okay, so we can use this to convert this into angular quantity, convert the L into angular quantity. So we have L, which was R cross P, which was R cross MV, and M is just doesn't, it's a scalar, so I cannot in the front part, M R cross V, and R V I can replace with that, R cross omega cross R. Now this is a triple product, so we can use a back cab rule, and we can write down as M, take this guy out first and take the dot product of the remaining other two, and then I take this guy out because of cab, which one to take out first, and then dot product of the other two. So this one is just M R square omega vector, and the other one is actually I need to compute this. So this is the L written as angular velocity, in terms of angular velocity. Often it's not very useful for a particle, but this is the one that we use for rigid body motion. So the L, to summarize, you have R cross MV, which is also M R square omega minus M R dot omega R. So this is for a particle about O, because this R is displacement vector from O. Okay, so the other thing that we want to address is angular momentum of a rigid body. That's the one goes into problems, right? So angular momentum of a rigid body. Angular momentum of a rigid body. So what is a rigid body? A rigid body is a collection of particles with fixed relative positions. So like if you have a box, and it's got a whole bunch of masses everywhere, but they're not moving around with respect to each other. So this one and this one remain the same. The entire box is moving with respect to this point O, but this distance, this relative position of these guys are the same over here as this over here. So that's the rigid body. You can have a disk, maybe rotating about this. You can think of this as a whole bunch of particles, but the relative position is not changing with time. Of course, the orientation in space is changing in time, but not relative position. So you that's what defines a rigid body. So how do you say angular momentum rigid body? Well, so over here is angular momentum versus each single point mass, and this one has a whole bunch of point masses. So what we do, imagine what we do is L of the rigid body about some O will be sum of all the particles here. So sum of about I for the particles, I equals say 1 through n particles. N can be very large, n can be, however, n is infinite here, and maybe you have a box where these are light rods and you can ignore their masses, and all the masses are just at the corners. So the n will be 8 here, and the rods we can light and ignore rods, and so you'll have M1, M2, and so M8, so like that. So you go all the way to that many, each of the masses, and for each of the masses you'll have this guy. So this is a vector, so I will end up with Mi, say first mass, is displacement square omega. So omega is going to be same for everybody, so I will have this as omega, and then we'll have Mi, I equals 1 through n, and this is Ri, but omega will be the same. Omega is independent of the particle. Omega of all particles of a rigid body, same. This is very important. This you can prove this. I'm not going to prove it, but it just take it as a result. So omega is same, and Ri. So this is the detail of what the angular momentum will look like, but we can actually simplify it and write in a much more compact notation. So let me do that, and I'll give you a more compact formula for this. Okay, so I took time to write this out in detail, so let me go over that. So I'm looking at the kth component of this vector. So k can be 1 for the x component, k equals to 2 for the y component angular momentum, and k equals to 3 for the z component. So pick k according to what component angular momentum I want, and then so this where the k ends up from this, and then if this one Ri, the ith particle displacement vector, I will need the kth component of this. Now the dot product, I can write dot product as a, ith particle L, so like Ri1 will be its x coordinate, Ri2 will be its y coordinate, Ri3 will be its z coordinate, and so it has to be summed over. This is the dot product, and then I try to introduce a Kronecker delta. So what is this delta? So that I can use the sum. In this sum, because of Kronecker delta, this is same as that. So Kronecker delta KL means is 1 if this index, each one of them is going through 1 to 3 and 1 to 3. If k equals to L, then it's 1, otherwise 0 if k not equals to L. So there's only, if I sum over L, I'm going to get only 1 out. So this is a nice way to combine terms. So we have a actually angular momentum on the x component will go over the angular velocity of all three. This is very important observation. So if I were to write L x component, I will get I will get over all particles I equals 1 through n, and say I sum over this, what I'm going to get? I'm going to get mi, ri square will be xi square plus yi square plus zi square, and L, I'm summing over L, so I want x. So when k is x, when this is x, I'm only time I'm going to get is when L is x. So this will be omega x, and then from the second term, when I summed over L, I'm going to get mi. When L is 1, I get x, so I get xi, and then k is already x, so this is xi omega x. But when L is another term I'm going to get is mi, L is 2, k is still x, so I get a yi xi omega y, because this one goes together, this goes with that, and then I'm going to get another term mi zi omega z. So this will cancel this guy, and so I have here I equals 1 through n. I got mi y square plus zi square omega x. Then I have a minus mi xi yi omega y plus minus mi xi zi omega z. So we have just x component angular momentum depends on x velocity, y angular velocity, and z angular velocity. So if I combine all of this, so L may not be in the same direction as omega. Recall linear momentum p, same direction as v, but for L it may not happen. This is one of the complications that happens. Now to name this quantity here, this quantity here, and this quantity here, they're what is called moment of inertia. They're parts of moment of inertia. So this is a moment of inertia that's labeled Ixx. This moment of inertia is called xy, and this moment of inertia is called Ixz. So when we have a full angular momentum, so the full angular momentum, you'll have a Lx component and Ly component and Lz component. So this will have its own angular momentum Ixy, Iyy, and Iyz. And this similarly, if you work this out, this is going to turn out to be Ixz and Iyz and Izz. So in general, what you are going to get is going to be 1, 2, 3, 4, 5, 6, 7, 8, and 9 moment of inertia. That's like too complication, right? We would like to deal with simpler cases, so we deal with what is called principal axis, and in situations like say you have a spherical ball, and if the axes are taken to be through the center, then no matter you rotate about this, I wrote it apart. This any axis direction is the same. So in this case, you take a x, y, and z axis. Then when you work this out, you find that off-centered guy ij equal to 0 when I is not equal to j. So all of these guys will be 0, and I is I think 3/5 if this is mass and radius r square. I equals to 1, 2, 3. So just these guys are these are the these guys. These three guys are non-zero. When you work out in this case, what will happen? Okay, when you have all the zero, then it's very simplifies. Then in this case, you get Lx is equal to 3/5. There's m here. mr square omega x. Ly equals to 3/5 mr square omega y. Lz is 3/5 mr square omega z. And then L is parallel to omega here. Let's look at another example. Okay, let's take another example. Another example will be a disk. So radius r and mass m, and this height is much less than r, so you kind of ignore h. Okay, so here is a one principal axis, and just right to the center another principal axis. Maybe this is y, this is x, and then this is the z-axis. So if you were to look at the moment inertia, ij here will be 0 for I not equal to j. But when you look at just the z-axis, so rotation about that just turns out to be half mr square. If I rotate about this, ixx can be, you can see this axis and this axis will be symmetric. So this will be iyy, and that's going to be 1/4 mr square. Now, if you had a actual cylinder, you could ignore the h, and this is r. This is z-axis, and then you have y here and x here. So again, ij will be 0 if I not equal to j. Izz will still be the same as that because it's stacked up the same way. So this will be half mr square, but ixx and iyy will be more than that, because now you have it's spread out over this and the whole thing will rotate. So you'll have, it's going to be 1/4 mr square, but then you have to add mh square to that. So in both cases, you can see that ixx equal to iyy, and let's call it I1, and this one is I3. So when you in these cases, when you write down angular momentum, it's going to be I1 omega x hat plus I1 omega y hat plus I3 or I3 omega z hat. These are unit vectors like I hat, k hat, j hat. These are the guys. And of course, this is not parallel to omega x hat plus omega y hat plus omega z hat. this is what the omega direction is. So omega direction is that way, then L direction may be that way, not same direction. And this is unlike P and B. These guys are always same direction. So just make sure that you understand that this thing is very important. Well, I'm going to stop here, and just to remind you that you can get more at this website, physicsbootcamp.org, and remember to subscribe to the channel. Subscribe to this channel. That helps distribute this video a little more widely. I'm going to stop here. Later on we're going to do some problems, calculate some of the moment of inertia and use it in problem. Okay, so talk to you later. Bye bye.